Now in this lecture we'll find out the radius of the circle using two different methods. In the drawing we have a circle. Inside this, we know that the center of this circle is at point O here. Line segment AB equals to 6 units. Line segment BC equals to 13 units. Line segment AD equals to 18 units in its length. Angle BAD, this angle equals to 90 degrees. Angle ABC, this angle equals also to 90 degrees. And our mission is to find out the radius of this circle. Okay, so first of all, we will make a construction. From point C, we will draw perpendicular on AD. Okay, so here this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD as E. Here we actually created quadrilateral ABEC. Inside quadrilateral ABEC we have 1, 2, 3 right angles. The sum of 3 right angles is 90 degrees times 3 is 270 degrees, plus the missing angle, that is this angle. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle, that is to say angle ECB, this angle must be equal to 90 degrees, according to the rule that I mentioned. And so quadrilateral ABEC has 4 right angles, therefore quadrilateral ABEC is a rectangle. And you know that the opposite sides of a rectangle are equal to each other, that is to say AB equals to EC, but AB equals to 6 according to what is given as a question. Therefore AC will be also equal to 6 units. Likewise, according to the sum rule that the opposite sides of a rectangle are equal to each other, we will get that BC equals to AE, but BC equals to 13 units, therefore EA must be also equal to 13 units. Okay, in the next step, we will join points D and C together by a straight line. By joining points D and C, we created here a triangle, the right triangle ECD. This right triangle, the right triangle ECD. So we'll implement the Pythagoras theorem on the green right triangle, triangle ECD. So here, the right triangle, triangle ECD, by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the green right triangle ECD is DC, therefore the square of the hypotenuse is DC squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EC squared plus ED squared. In conclusion, we found out that according to the Pythagoras theorem, DC squared equals to EC squared plus ED squared. That is to say, DC squared, that is the square of the hypotenuse, must be equal to EC squared. EC equals to 6 units, as you can see here. Therefore, EC squared equals to 6 squared, that is 36, plus ED squared. So here, what is the value of ED? Here, ED, it is equal to AD minus AE. Again, AD minus AE equals to ED. That is to say, ED equals to AD, that is 18, minus AE, that is 13. 18 minus 13 is 5. So ED equals to 5 units. So ED equals to 5 units, therefore ED squared equals to 5 squared, that is 25. In conclusion, we found out that DC squared, that is the square of the hypotenuse, equals to 36 plus 25. 36 plus 25, it is equal to 61. So DC squared equals to 61. We take a root out of this equation and we get that DC equals to the square root of 61. So we found out that the hypotenuse here, DC, it is equal to the square root of 61. In the next step, we will join points B and D together by a straight line. By joining points B and D, we created here triangle, the right triangle BAD. In the right triangle, triangle BAD, this right triangle, by PT is the evaluation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle is BD, therefore the square of the hypotenuse is BD squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to AB squared plus AD squared. Repeat again, according to the Pythagoras theorem, in the right triangle ABD, BD squared equals to AB squared plus AD squared. So BD squared, that is the square of the hypotenuse, in the right triangle ABD, must be equal to AB squared. AB equals to 6, therefore AB squared equals to 6 squared, that is 36, plus AD squared. AD equals to 18, as you can see here. AD equals to 18, according to what is given as the equation, therefore AD squared equals to 18 squared, that is 324. In conclusion, we found out that BD squared, that is the square of the hypotenuse in the right triangle ABD, is equal to 36 plus 324, it is 360. So BD squared equals to 360. We take a root out of this equation and we get that BD, that is the hypotenuse in the right triangle BAD, it is equal to the square root of 360, but we know that BD, that 360 is 36 times 10, so we substitute 360 by 36 times 10, so BD, the hypotenuse BD, it is equal to the square root of 36 is 6, so we'll take out 36 out of the root and we'll substitute it by 6, because the square root of 36 is 6. So inside the root we're left only with 10. So in conclusion, we found out that BD, that is the length of the hypotenuse, equals to 6 times square root of 10. Here BD equals to 6 times square root of 10 units. Okay, so in the next step we'll calculate the area of the green triangle BDC or BCD. The area of the green triangle BCD here the squared bracket is the sign for the area. It means the area of triangle BCD. It will be equal to the base of the triangle times the height to the base over 2. I must emphasize that the height to the base must create 90 degrees with the base. Okay? So the area of triangle BCD, the green triangle BCD, will be equal to the base. We'll choose the base as BC. BC is the base of the triangle. So we substitute the base by BC times the height. The height. So we will extend side BC by a straight line, and from point D we will draw perpendicular on the extended BC. And this will be the height. Why? Because the height creates 90 degrees with the extended BC. This angle equals to 90 degrees, and this angle equals to 90 degrees. We define the touching point of the perpendicular from point D in the extended BC as F. That is to say, DF is the height to the base. Here, by drawing this perpendicular DF, we created here quadrilateral ABDF. Inside quadrilateral ABDF, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And because of the fact that inside quadrilateral ABDF we have 4 right angles, therefore quadrilateral ABDF is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to DF. AB equals to DF. But it is given us in the question that AB equals to 6 units. Here AB equals to 6. And from this equation, 6 equals to AB equals to DF, we will derive that DF is also equals to 6 units. That is to say, the height DF equals to 6 units. Now, we can find the area of the green triangle BDC. The area of the green triangle BDC equals to the base BC times the height, that is equal to 6 units, according to what we have already found out here, over 2. So it is equal to BC. BC equals to 13 units, so we substitute BC by 13 times 6 over 2. 6 over 2 is 3, and 3 times 13 is 39. So in conclusion, we found out that the area of the green triangle BCD, it is equal, here the area is equal to 39 square units. Okay. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. According to the new rule, that will be rule number 1. Actually, I will draw the drawing of the rule number 1. Here we have a circle. Inside this, the center of the circle is at this point, and inside this circle we have a triangle ABC that is blocked by the circle. Here this is triangle ABC. that it is blocked by the circle. The length of side AB equals to A units, side BC equals to B units in its length, and side AC equals to C units in its length. So you can see here that the circle blocks triangle ABC. What is the definition of any triangle that is blocked by a circle? Only and only if all the three vertices of the triangle are touching the circle, only then you can say that the triangle is blocked by the circle. As you can see here, this vertex is touches the circle at point A, this vertex is touches the circle at point B, and this vertex touches the circle at point C. Therefore, we can say that the triangle ABC, this triangle, it is blocked by the circle. Okay? So, the rule is that if triangle ABC is blocked by a circle like we see in the drawing, and we define the radius of this circle here. O is the center of the circle, M is the point of the circle itself, therefore OM is the radius of this circle that we will define as capital R. Then the radius of the circle, the radius of the circle that blocks the triangle then the radius capital R. So capital R will be equal to the multiplication of the side lengths of the triangle. The length of side AB is A, the length of side BC is B, so it is A times B, and the length of side AC is C. So it is A times B times C. This is the multiplication of the side lengths of the triangle ABC by each other over 4 times of the area of triangle ABC. Okay? So the radius of any circle that is blocked by the radius of any circle that blocks a triangle will be equal to the multiplication of the side lengths of the triangle by each other over 4 times the area of the triangle that is blocked by the circle. So actually we can implement rule number 1 in our drawing. Why? Because in our drawing we have a triangle BDC, the green triangle BDC is blocked by a circle, by the circle. That is to say, we can implement here rule number 1. And so according to rule number 1, we will get that the radius that we are looking for, that is to say the radius of this circle, so we will define the radius of this circle as capital R. That is to say OM equals to capital R. Then according to rule number 1, we will get that capital R equals to the multiplication of the left sides of the triangle by each other, that is to say BC times CD times DB over 4 times the area of triangle BDC. Repeat again. In our original drawing, the green triangle, triangle BDC, this green triangle is blocked by the circle. Why it is blocked by the circle? Because of the fact that this vertex touches the circle at point B, this vertex of the triangle touches the circle at point C, and this vertex touches the circle at point D. Therefore, we can say for sure that the green triangle BDC is blocked by this circle. Therefore, we can implement here rule number 1. And according to rule number 1, the radius of this circle that blocks triangle BDC, the green triangle, that is to say capital R, will be equal to the multiplication of the side lengths of the triangle by each other, that is to say BC times CD times DB, over 4 times the area of this triangle, triangle BDC. So actually capital R equals to BC, BC equals to 13 times CD, CD equals to the square root of 61, and finally DB equals to 6 times square root of 10 units over 4 times the area of the green triangle, triangle BDC. We have already found out that the area of the green triangle, triangle BDC equals to 39 square units. So we found out the radius that we are looking for, the radius of this circle that blocks the triangle BDC. Here we will divide both the numerator and the denominator of this expression by 13. And we will get that capital R, that is the radius of the circle that we are looking for, it is equal to 13 over 13 is 1, so 13 will get cancelled. We left only with square root of 61 times square root of 10 times 6 over 4 times 39 over 13 is 3. Okay. So actually found out that the radius of the circle that we are looking for equals to the square root of 61 times square root of 10 times 6 over 3 times 4. 3 times 4 is 12, so we write down that the radius of the circle that we are looking for, that is to say capital R, is equal to the square root of 61 times the square root of 10 times 6 over 4 times 3 is 12. Here we will divide both the numerator and the denominator of this expression by 6. So in the numerator we have 6, so 6 over 6 is 1, so 6 will get cancelled. So we get that R equals to, in the numerator we left only with the square root of 61 times square root of 10, because 6 get cancelled, over 12 over 6 is 2. Okay, so capital R equals to the square root of 61 times square root of 10 over 2. According to the algebraic identity that the square root of A times square root of B it is equal to the square root of A times B, we will get that capital R equals to the square root of 61 times the square root of 10, according to this trigonometric, to this algebraic identity, will be equal to the square root of 61 times 10, that is 610 over 2. So I found out that the radius that we are looking for, the radius of this circle, that is to say capital R, equals to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. Okay, so we finish with the first method. In the next step I will present to you the second method to find out the area, the radius of this circle. Okay. So I will not repeat on the same thing that we have already found out in the first method. Here from point C we draw perpendicular on AD. So this angle equals to 90 degrees, and this angle equals also to 90 degrees according to our construction. We define the touching point of the perpendicular from point C on AD as E. And actually quadrilateral ABEC is a rectangle. This angle equals to 90 degrees. The opposite sides of a rectangle are equal to each other, that is to say AB equals to EC, but AB equals to 6, therefore EC also equals to 6. And AE equals to BC, but BC equals to 13, therefore AE will be also equal to 13. And here ED, it is equal to AD minus AE, that is to say it is equal to 18 minus 13, that is 5. So, until this stage we done all the things in the first method. In the next step, from point O, that is the center of the circle, we will draw perpendicular on chord BC. So here, that is to say this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and BC as N, as capital N. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. Okay, so if we have a circle, that could be any circle. And the center of this circle is at point O. And we have a chord BC. Chord BC could be any chord. And from point O, that is the center of the circle, we will draw perpendicular on chord BC. That is to say, here this angle equals to 90 degrees, and this angle it is also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point O on BC as M. According to this rule, that is actually rule number 1, the perpendicular from point O on BC, that is to say the perpendicular OM, bisects chord BC. That is to say, BM, it is equal to MC. Okay? So whenever from the center of the circle you draw perpendicular to any chord, that perpendicular will bisect the chord. Here we draw perpendicular on chord BC, therefore the perpendicular OM bisects chord BC. That is to say BM equals to MC, very simple. So we can actually implement rule number 1 in our drawing. Why? Because in our drawing we have from the center of this circle, that is to say from point O, we have perpendicular ON on chord BC. Therefore the perpendicular ON bisects chord BC. That is to say BN equals to NC. So I write it down. In our original drawing, we actually have ON is perpendicular to chord BC. I will write it down. ON, line segment ON is perpendicular to chord BC. And because of the fact that ON is perpendicular to BC, we can implement here rule number 1. And according to rule number 1, the perpendicular ON bisects BC. That is to say, BN equals to NC. BN equals to NC according to rule number 1. Okay? In the next step, actually we will define the perpendicular from point O and AD, or the touching point of the perpendicular from point O and AD as point M. So in the next step we will focus on quadrilateral ABMN. Quadrilateral ABMN. ABMN. In quadrilateral ABMN, this quadrilateral, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And because of the fact that quadrilateral ABMN has 4 right angles, therefore quadrilateral ABMN is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, AM equals to BN. AM equals to BN. In the next step, we will focus on quadrilateral MNEC, the lower quadrilateral MNEC. In quadrilateral MNEC, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. I repeat again that this angle equals to 90 degrees according to our construction. From point C we draw perpendicular on AD, therefore this angle equals to 90 degrees. And because of the fact that ABCE as 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. That is to say, this angle also equals to 90 degrees. Therefore, in quadrilateral MNEC we have 1, 2, 3 right angles. Therefore, the fourth angle, this angle, must be also equal to 90 degrees. That is to say, in quadrilateral MNEC we have 4 right angles, and because of the fact that in quadrilateral MNEC we have 4 right angles, quadrilateral MNEC is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle MNEC, side ME equals to NC. Side ME equals to NC. Okay, so we can actually summarize what we have already found out until now. According to rule number 1, we found out that BN equals to NC. BN equals to NC. But here we found out that NC equals to ME. So we can write here that NC equals to ME. And we also found out that BN equals to AM. So we can write here that BN equals to AM. So from this long equation, AM equals to BN equals to MC equals to ME, we will derive that AM equals to ME. AM equals to ME. AM equals to ME. AM equals to ME. Here we will derive that AM equals to ME. In the next step, we will extend line segment DA until it touches the circle, and we define the touching point of the extended line segment DA and the circle as point F. By extending line segment DA, we created here a chord FD. Okay, and here ON is perpendicular to BC. ON is perpendicular, it must be a straight line. So if we focus on the upper side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of ON at point M? We have this angle that is equal to 90 degrees, plus the missing angle. In total they must be equal to 90 degrees. Therefore the missing angle, that is to say this angle, must be also equal to 90 degrees. Likewise, we will focus on the lower side of the straight line AN at point M. On the lower side, the sum of the angles must be also equal to 90 degrees at point M. So which angles we have at the lower side of ON at point M? We have this angle that is equal to 90 degrees, plus the missing angle. In total, they must be equal to 180 degrees. Therefore, the missing angle must be equal to 90 degrees in order to complete the sum of the angles on the lower side of ON at point M to 180 degrees. The missing angle must be also equal to 90 degrees. So we actually found out that OM is perpendicular to FD. OM is perpendicular to FD. Why? Because this angle equals to 90 degrees and this angle equals to 90 degrees. So I write it down. We actually found out that OM, that is the line segment that exists from the center of the circle, from point O, is perpendicular to chord FD. OM is perpendicular to FD. Therefore, we can implement here rule number 1. Whenever we have from the center of the circle any perpendicular to any chord, like here, the perpendicular bisects the chord. That is to say, FD is bisected by OM. That is to say, FM equals to MD. Okay, FM equals to MD according to rule number 1. So again, FM equals to MD according to rule number 1 because of the fact that OM, the perpendicular from the center of the circle, that is OM, bisects FD. Therefore, FM equals to MD. But what is the value of FM? What is the value of FM? It is very easy to see from the drawing that FM equals to FA plus AM. So we can substitute FM by FA plus AM. And FM equals to MD. What is the value of MD? From the drawing it is very easy to see that MD equals to ME plus ED. So we actually substituted MD by ED. So in conclusion we found out that FA plus AM, that is FM, equals to ME plus ED, that is MD. Okay? But because of the fact that we have already found out that AM equals to ME, here AM equals to ME. So we can cancel those two line segments because they are equal to each other. And we left only with FA that is equal to ED. Here we found out that FA equals to ED. But we have already found out that ED equals to 5 units. ED equals to 5 units, and from this equation FA equals to ED equals to 5, we will derive that FA is also equals to 5 units. FA equals to 5 units. In the next step, we will extend line segment BA or side BA until it touches the circle, and we will define the touching point of the extended side BA and the circle as point P. In the next step, we will implement in our drawing the old new rule, rule number 2. I will remind you what is the old new rule, rule number 2. According to the old new rule, rule number 2, if we have chord AB that intersects with chord CD at point O, point O is the intersection point between the two chords, then we will get that AO times OB equals to CO times OD. AO times OB equals to CO times OD. So we actually can implement rule number 2 in our rule number 2 in our drawing. Why? Because in our drawing we have chord FD intersects with chord PB, this is chord PB, at point A. The intersection point occurs at point A, between the two chords. Okay, I repeat again. Chord FD in our regular drawing intersects with chord PB at point B, at point A. Therefore, according to the old rule, rule number 2, we will get that FA times AD equals to PA times AB. PA times AB. Repeat again. According to the old rule, rule number 2, we will get that FA times AD equals to PA times AB. Again, FA times AD equals to PA times AB. FA equals to 5 units, AD equals to 18 units. Here, AD equals to 18 units, according to what is given us the question. PA is the missing line segment, so we will leave it as it is. And finally, AB equals to 6 units. So we actually found out that according to the old rule, rule number 2, 5 times 18 equals to PA times 6. Here we will divide this equation by 6, and we'll get that 5 times 18 over 6 equals to PA. That is to say, PA, the line segment that we are looking for, PA equals to 18 over 6 is 3, and 3 times 5 is 15. So we found out that the missing chord PA equals to 15 units. In the next step, I will present to you a new rule that will be actually rule number 4, and we will implement rule number 4 in our drawing. According to rule number 4, if we have a circle that could be any circle, this is a circle, and in this circle we have chord AB. This is chord AB, and chord AB, it is actually intersects with chord CD. This is chord CD, and and they intersect with each other, they create between them 90 degrees at the intersection point. The intersection point will be defined as point O. So here chord AB intersects with chord CD at 90 degrees at point O. So I write it down. If chord AB intersects with chord CD at 90 degrees, and the intersection point occurs at point O. Then the following equation will be true. We will define the radius of this circle as capital R. Here, this is the center of the circle. We'll define the center of this circle as point E, and a point on the circle itself here is point M. So EM is the radius of the circle that we will define as capital R. So if we know that chord AB intersects with chord CD at 90 degrees, then the following equation will be true. That 4 times capital R squared, capital R is the radius of this circle, will be equal to AO squared plus OB squared plus CO squared plus OD squared. I'll repeat again. If we know that chord AB intersects with chord CD at 90 degrees, then AO squared plus OB squared plus CO squared plus OD squared equals to 4R squared, or 4 capital R squared. Capital R equals to the radius of this circle. Okay, so we can actually implement rule number 4 in our drawing. Why? Because of the fact that in our drawing we have chord FD, this is chord FD, intersects with chord PB, this is chord PB at 90 degrees. That is to say, at the intersection point, that is point A, they create between them 90 degrees. This angle equals to 90 degrees. Therefore, and it happens at point A. That is to say, we can implement here rule number 4. And according to rule number 4, we define the radius of this circle as capital R. This is point M. OM equals to capital R. So 4 times R squared, again capital R is the radius of the circle according to rule number 4, 4 times R squared equals to FA squared plus AD squared plus PA squared plus AB squared. Repeat again. Now, when you are drawing, we have chord FD that intersects with chord PB at 90 degrees at point A. Therefore, according to rule number 4, 4 times R, capital R squared, capital R is the radius of the circle, equals to FA squared plus AD squared plus PA squared plus AB squared. So 4 times R squared, it is equal to FA squared. FA equals to 5, therefore FA squared equals to 5 squared, that is 25, plus AD squared. AD equals to 18, therefore AD squared equals to 18 squared, that is 324, plus PA squared. PA equals to 15, therefore PA squared equals to 15 squared, that is 225, plus AB squared. AB equals to 6, therefore AB squared equals to 6 squared, that is 36. In conclusion, we found out that 4 times capital R squared equals to 25 plus 225 is 250, plus 36 plus 324, which is 360. So 4R squared equals to 250 plus 360, it is equal to 610. We will divide this equation by 4, and we will get that R, capital R squared equals to 610 over 4. Here we will take a root out of this equation, and we will get that capital R, that is the radius of the circle that we are looking for, it is equal to the square root of 610 over 4. That is to say, capital R equals to the square root of 610, and the square root of 4 is 2. So in conclusion, we found out that the radius of this circle, the radius that we are looking for, is equal to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. And that is the answer to the question according to the second method. In the next step, I will summarize the lecture. Okay. We'll start with the first method. So in the drawing we have a circle. The center of the circle is at this point, point O. Inside the circle we have line segment AB that is equal to 6 units. We have line segment AD that is equal to 18 units. And we have line segment BC that is equal to 13 units. Angle BAD, this angle equals to 90 degrees, and this angle actually ABC equals to 90 degrees also. Our mission is to find out the radius of this circle, that is actually OM, that is equal to capital R according to our definition. So first of all, from point C we drew perpendicular on AD. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD is E. So actually we created here, by the construction we created here quadrilateral ABEC. In this quadrilateral ABEC we have 1, 2, 3 right angles. According to the sum of 3 right angles is 270 degrees, and according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees, the fourth angle must be also equal to 90 degrees. And because of the fact that inside quadrilateral ABEC, this quadrilateral we have 4 right angles, therefore quadrilateral ABEC is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to EC, but AB equals to 6, therefore EC also equals to 6. According to the same rule that the opposite sides of a rectangle are equal to each other, we get that BC equals to AE, but we know that BC equals to 13 units according to what is given as the question. Therefore AE is also equals to 13 units. Okay, and here, what is the length of line segment ED? ED equals to AD minus AE. AD equals to 18 units, AE equals to 13 units. So AD minus AE equals to 13 minus 18 minus 13, that is 5. So we found out that ED equals to 5 units. In the next step we actually connected points D and C together by a straight line, and we actually implemented the Pythagoras theorem on the green small right triangle ECD. Okay, so in the small green right triangle ECD, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here PT is a version for Pythagoras theorem. The square of the hypotenuse, this is the hypotenuse, therefore the square of the hypotenuse is this C square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EC square plus AD square. In conclusion, we found out that DC square equals to EC square plus AD square. So DC square, that is the square of the hypotenuse, equals to EC square. EC equals to 6, therefore EC square equals to 6 square, that is 36. Plus AD square. AD equals to 5, therefore AD square equals to 5 square, that is 25. So in conclusion, we found out that DC square equals to 36 plus 25, that is 61. That is to say, DC equals, if DC square equals to 61, we took a root out of this equation and we found out that DC equals to the square root of 61. So the hypotenuse DC here, it is equal to the square root of 61 units. In the next step, we will join points B and D together by a straight line. By joining points B and D, we actually created the right triangle BAD. We implemented the Pythagoras theorem on the right triangle BAD. By PT is a version for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars in any right triangle. The hypotenuse in the right triangle BAD is BD. Therefore, the square of the hypotenuse is BD square, and it must be equal to the sum of the squares of the perpendiculars. That is to say it must be equal to AB square plus AD square. So in conclusion, we found out that in the right triangle BAD, according to the Pythagoras theorem, BD square equals to AB square plus AD square. So BD square is equal to AB square. AB equals to 6, therefore AB square equals to 6 square, that is 36. Plus AD square. AD equals to 18, therefore AD square equals to 18 square, that is 324. So in conclusion, we found out that BD square equals to 36 plus 324. Okay, and 36 plus 324 is 360. So we found out that BD square equals to 360. We took a root out of this equation and found out that BD equals to the square root of 360, but 360 is 36 times 10. So we substituted 360 by 36 times 10, and we found out actually that BD equals to the square root of 36 times 10. We took 36 out of the root. That is to say, the square root of 36 is 6. So in conclusion, we found out that BD equals to 6, and inside the root we left only with 10. So BD, that is the hypotenuse, it is equal to 6 times square root of 10 units in its length. Here BD, that is the hypotenuse of the right triangle ABD, it is equal to 6 times square root of 10 units. Okay? In the next step, we found out the area of the green triangle BCD. The area of the green triangle BCD equals to the base of the triangle times the height to the base over 2. I must emphasize that the height to the base must create 90 degrees with the base. And we choose the base of the green triangle BCD as BC. So we substituted the base by BC times the height over 2 is the area of the green triangle. So first of all, we have to find out the area, the length of the height, the value of the height in the green triangle BDC. Because of the fact that BC is the base of the green triangle, we will extend BC. We extended BC by a straight line, and then from point D, that is the vertex, one of the vertices of the green triangle BDC, from the vertex D, we drew perpendicular on the extended BC. That is to say, this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. we define the touching point of the perpendicular from point D and the extended BC as F. Okay, so because of the fact that DF is perpendicular to the extended BC, it means that DF it is actually the height to the base BC. Why? Because it creates 90 degrees with the extended BC. And then we focused on quadrilateral ABDF. On quadrilateral ABDF, we have 1, 2, 3 right angles. And therefore, the fourth angle must be also equal to 90 degrees. So I will not repeat on it. And because of the fact that in quadrilateral ABDF we have 4 right angles, it means that quadrilateral ABDF is a rectangle. But we also know here quadrilateral ABDF is a rectangle. Why? Because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. That is to say AB equals to DF. AB equals to DF. But according to what is given as the equation, AB equals to 6. So we can write here that AB equals to 6. And from this equation, 6 equals to AB equals to DF. We will derive that DF is also equals to 6 units. That is to say DF, that is the height to the base BC, equals to 6 units. Now we can calculate the area of the green triangle BCD. The area of the green triangle BCD equals to the base, that is BC, times the height to the base, that is 6, over 2. BC equals to 13 units, times the height, that is 6, over 2. 6 over 2 is 3, and 3 times 13 is 39. In conclusion, we found out that the area of the green triangle BCD equals to 39 square units. Okay, the area of this green triangle BCD equals to 39 square units. Then, here, we actually extended. Here we calculated, so we know that the area of the green triangle BCD, is equal to 39 square units. Then I presented to you rule number 1, and we implemented rule number 1 in our drawing. According to rule number 1, if triangle ABC, this is triangle ABC, that is blocked by this circle. Why it is blocked by the circle? Because of the fact that all the 3 vertices of the triangle touching the circle at points A, C, and B. So here we have triangle ABC that it is blocked by this circle. Then the radius of this circle, that is OM, and it is equal to capital R according to our definition, will be equal to, here, the length of side AB is A units, the length of side BC is B units, and side AC equals to C units in its length. So the radius of the circle that blocks triangle ABC will be equal to A times B times C. That is the multiplication of the side lengths of the triangle by each other, over 4 times the area of triangle ABC. So we can actually implement rule number 1 in our drawing. Why? Because of the fact that in our drawing we have the green triangle BDC. This green triangle, it is blocked by this circle. Why? Because this vertex touches the circle at point B, this vertex touches the circle at point C, and finally this vertex touches the circle at point D. Therefore, we can definitely say that the green triangle BDC, it is blocked by this circle. And for that reason, we can implement here rule number 1. I'll repeat again, the green triangle BDC is blocked by a circle, and therefore, according to rule number 1, we will get that the radius of this circle that is equal to capital R, according to our definition, will be equal to BC times CD times BD. That is actually the multiplication of the side lengths of the triangle by each other over 4 times the area of the green triangle BDC. This is according to rule number 1. So capital R equals to BC is 13, CD is square root of 61, and DB equals to 6 times square root of 10 over 4 times of the area of triangle BDC. The area of triangle BDC equals to 39 square units. Okay, so here, so this is the radius of the circle that blocks the green triangle BDC. Here we simplify this expression by dividing both the numerator and the denominator by 13. 13 over 13 is 1, so 13 will get cancelled. So in the numerator we left only with square root of 61 times square root of 10 times 6 over 4 times 39. And 39 over 13 is 3. So in conclusion, in the denominator we left only with 3 times 4. Therefore, we found out that the radius of the circle that blocks the green triangle BDC equals to the square root of 61 times square root of 10 times 6 over 4 times 3. 4 times 3 is 12. So in conclusion, we found out that the radius of the circle that blocks the green triangle BDC equals to the square root of 61 times the square root of 10 times 6 over 12. We divided both the numerator and the denominator of this expression by 6. In the numerator we have 6, so 6 over 6 is 1, so 6 will get cancelled. So in the numerator we left only with square root of 61 times square root of 10, and 12 over 2 is 6. So in conclusion, we found out that the radius of the circle that blocks the green triangle BDC equals to, capital R equals to the square root of 61 times square root of 10 over 2. According to the algebraic identity that the square root of A times square root of B equals to the square root of A times B, we will get that the square root of 61 times the square root of 10 equals to the square root of 61 times 10. 61 times 10 is 610. So inside the square root we left with 610 over 2. In conclusion, we found out that the radius of this circle, it is equal to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. So we finished with the first method. Then I presented to you the second method. The second method, we did the same thing as we did in the first method, that is to say, from point C we do perpendicular on AD, that is to say this angle equals to 90 degrees, this angle equals to 90 degrees, according to our construction. We define the touching point of the perpendicular from point C and AD is E. So by doing this construction, we actually created here quadrilateral ABEC. This quadrilateral ABEC has 1, 2, 3 right angles. The sum of, so I'll not repeat on it. And because of the fact that quadrilateral, we did it already in the first method, because of the fact that quadrilateral ABEC has 3 right angles, therefore the fourth angle must be also equal to 90 degrees. That is to say, this angle must be equal to 90 degrees. So that is to say, inside quadrilateral ABEC we have 4 right angles, and therefore quadrilateral ABEC is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to EC, but we know that AB equals to 6 units, therefore EC also equals to 6 units. According to the same rule that the opposite sides of a rectangle are equal to each other, we will get that BC equals to AE. But BC equals to 13 units according to what is given us in the question. Therefore, AE also equals to 13 units. Okay? What is the length of ED? According to what we have already done In the first method, here ED equals to AD minus AE. That is to say, it is equal to 18 minus 13, that is 5. So ED equals to 5 units. Then, from point O, we drew perpendicular on chord BC. Then I presented to you rule number 1, and we implemented rule number 1 in our drawing. According to rule number 1, if we have this circle, point O is the center of the circle, and BC is chord that could be any chord inside the circle. From point O, that is the center of the circle, we draw perpendicular on BC. That is to say, this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We defined the touching point of the perpendicular from point O and BC as M. So we have OM, that is perpendicular to BC. And because of the fact that from the center of the circle we have perpendicular on chord BC, the perpendicular OM bisects chord BC. That is to say, BM equals to MC. BM equals to MC. We actually can implement rule number 1 in our drawing. Why? Because of the fact that in our drawing we have perpendicular ON on chord BC. Perpendicular ON on chord BC. And according to rule number 1, the perpendicular ON bisects chord BC. That is to say, BN equals to NC. According to rule number 1, because of the fact that ON is perpendicular to BC, therefore perpendicular ON bisects BC. That is to say, BN equals to NC, according to rule number 1. We will focus on quadrilateral AB, MN. Inside quadrilateral AB, MN, we have this quadrilateral, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. And therefore, quadrilateral ABMN that has 4 right angles, it is a rectangle. Repeat again, quadrilateral ABMN is a rectangle because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, AN equals to BN. AM equals to BN. AM equals to BN. Then we focus on quadrilateral MNEC. In quadrilateral MNEC, we have 1, 2, 3 right angles. Why? Because first of all, ON is perpendicular to BC. That is to say, this angle equals to 90 degrees. And we have already found out that quadrilateral ABEC is a rectangle. That is to say, this angle it is also equals to 90 degrees. In conclusion, we have 1, 2, 3 right angles in quadrilateral MNEC, and therefore the fourth angle must be also equal to 90 degrees. That is to say, quadrilateral MNEC has 4 right angles, and therefore quadrilateral MNEC is a rectangle. Quadrilateral MNEC is a rectangle. We know that the opposite sides of a rectangle are equal to each other. That is to say, ME equals to NC. ME equals to NC. So we can summarize and say that according to rule number 1, we found out that BN equals to NC. But because of the fact that BN, it is also equals to AM, we can write here that BN equals to AM. And because of the fact that NC it is also equals to ME, we can write here that NC equals to ME. So from this long equation, AM equals to BN equals to NC equals to ME, we will derive that AM equals to ME. AM equals to ME. That is to say, AM equals to ME. Those two sides are equal to each other. Then we actually have from point O, we did the construction, we drew perpendicular on BC. So ON is a perpendicular, it is absolutely a straight line. ON is a straight line, and we know that the sum of the angles on one side of the straight line is equal to 180 degrees. So if we focus on the upper side of the straight line ON at point M, the sum of the angles must be equal to 180 degrees according to the rule that I already mentioned. So this angle equals to 90 degrees. So the missing angle must be also equal to 90 degrees in order to complete the sum of the angles on the upper side of ON at point M to 180 degrees. The missing angle must be also equal to 90 degrees. So this angle equals to 90 degrees. Likewise, if we focus on the lower side of the straight line ON at point M, here the sum of the angles must be also equal to 180 degrees. So which angles we have at the upper side of ON at point M? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. Therefore, the missing angle must be also equal to 90 degrees. In order to complete the sum of the angles on the lower side of the straight line ON at point M to 180 degrees, the missing angle here must be equal also to 90 degrees. So actually, we can conclude that line segment OM that exists from the center of the circle, that is to say from point O, is perpendicular to chord FD. Again, OM is perpendicular to chord FB because of the fact that this angle equals to 90 degrees and this angle equals to 90 degrees. Here we concluded that line segment OM that exists from the center of the circle is perpendicular to chord FD. Therefore, we can implement here rule number 1, and according to rule number 1, line segment OM bisect chord FD. Line segment OM bisect chord FD. That is to say, FM equals to MD. FM equals to MD according to rule number 1. So what is the value of FM? From the drawing, it is very easy to see that FM equals to FA plus AM. FM equals to FA plus AM. And what is the value of MD? From the drawing, it is very easy to see that MD equals to ME plus ED. MD equals to ME plus ED. So the FM equals to MD, it means that FA plus AM equals to ME plus ED. Okay? And we have already found out that AM equals to ME. Here AM equals to ME, therefore we can cancel those two line segments because they are equal to each other. And we left only with FA that is equal to ED. FA equals to ED. But we have already found out that ED equals to 5 units. Here ED equals to 5 units. And from this equation FA equals to ED equals to 5, we will derive that FA is also equals to 5. FA equals to 5. Then we actually extended line segment BA or side BA by a straight line until it touches the circle at this point, point P. Then we implemented here the old rule number 2. According to the old rule number 2, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can actually implement here the old rule number 2. Why? Because in our drawing we have chord FD that intersects with chord PB at point A. Repeat again. We have chord FD intersects with chord PB at point A. Therefore, according to the old rule 2, FA times AD equals to PA times AB. Repeat again, FA times AD equals to PA times AB according to the old rule number 2. FA equals to 5, AD equals to 18 units, PA is the missing line segment, so we leave it as it is, and AB equals to 6. In conclusion, we found out that 5 times 18 equals to PA times 6. Here we will divide this equation by 6, and we will get that PA equals to 5 times 18 over 6. 18 over 6 is 3. So in conclusion, this expression equals to 3 times 5, that is 15. That is to say, we found out that the length of line segment PA equals to 15 units. Here, PA equals to 15 units. Then I presented to you rule number 4, when we implemented rule number 4 in our drawing. According to rule number 4, if we have this circle, inside this circle we have chord AB. This is chord AB that intersects with chord CD, and the intersection point, they create between them 90 degrees. That is to say, this angle equals to 90 degrees. So whenever you have two chords that create the intersection point between them 90 degrees, you can implement rule number 4. Okay, so we have chord AB that intersects with chord CD at 90 degrees at point O. Therefore, according to the new rule, rule number 4, we will get that 4 times capital R squared. Capital R is the radius of this circle. It exists from the center of the circle, that is to say for point E, and that's the point M, that is the point of the circle itself. Therefore, EM is the radius of the circle, that is equal to capital R. So, if we know that chord AB intersects with chord CD at 90 degrees, then according to rule number 4, we will get that 4R squared equals to AO squared plus OB squared plus CO squared plus OD squared. Again, AO squared, 4 times R squared equals to AO squared plus OB squared plus CO squared plus OD squared. Okay, so we can implement rule number 4 in our drawing. Why? Because in our drawing we have chord FD that intersects with chord PB at 90 degrees at point A. Therefore, we can implement here rule number 4. I'll repeat again. We have chord FD that intersects with chord PB at 90 degrees at point A. For that reason, you can implement here rule number 4. Why? Because the two chords intersect with each other at 90 degrees. And according to rule number 4, we will get that 4 times capital R squared. Capital R is the radius of this circle because it starts from the center of the circle, that is to say from point O, and that's at point M, that is the point on the circle itself. So capital R, according to our definition, is the radius of this circle. So 4 times capital R squared will be equal to FA squared plus AD squared plus PA squared plus AB squared. I'll repeat again, according to rule number 4, we'll get that 4 times capital R squared equals to FA squared plus AD squared plus PA squared plus AB squared. So 4 times capital R squared equals to FA squared. FA equals to 5, therefore FA squared equals to 5 squared, that is 25, plus AD squared. AD equals to 18 units, therefore AD squared equals to 18 squared, that is 424, plus PA squared. PA equals to 15 units, therefore PA squared equals to 15 squared, that is 225, plus AB squared. AB equals to 6, therefore AB squared equals to 6 squared, that is 36. So in conclusion, we found out that 4 times capital R squared equals to 25 plus 225 is 250, and 324 plus 36 is 360. So 4 times capital R squared equals to 250 plus 360. 250 plus 360 equals to 610. In conclusion, we found out that 4 times capital R squared equals to 610. We divided this equation by 4, and we found out that capital R squared equals to 600 over 4. Here we took a root out of this equation and found out that capital R equals to the square root of 610 over 4. That is to say, capital R equals to the square root of 610, and the square root of 4 is 2. So we took 4 out of the root. So in conclusion, we found out that the radius of this circle, the radius that we are looking for, it is equal here, ON, that is capital R, it is equal to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. Okay, thank you very much.